Hello Year 11 and welcome to our 6th video here for Further Graphs. We're looking at inequalities today. We are going to solve inequality. It sounds like a grand aim, doesn't it? But it's really not as exciting as all of that. It is exciting, don't get me wrong. But the world will only be a marginally better place after we've solved this sort of inequality. So we have these things here. To begin with, what we want to do is to graph the solutions on number line, some rules about solving inequalities or inequations that maybe you remember. We can in many ways treat them like an equation. However, if we multiply or divide by a negative number, then we need to change the direction of the inequality. Same if we flip the left and right hand sides, as I often like to do when I'm solving equations. So we have to be careful which way that inequality is pointing. Now, here we have 5 minus 2x is less than 9. I'm going to start by subtracting 5 from both sides. Gives me negative 2x is less than 9 minus 5 is 4. Then I'm going to divide both sides by negative 2, and because I am dividing by a negative, I'm going to change the direction of that inequality sign. So I get x is greater than 4 divided by negative 2 is negative 2. Okay. Now, on a number line, because this is strictly greater than, I will need an open circle because it's not equal to. There's my negative 2, and it's those things that are bigger than negative 2, greater than negative 2, so it points to the right. Some people like to remember the little arrow on the end is the same shape as my inequality sign. That might be a little juvenile, but anyway, we have another one here. Where we're sandwiched between two values. So to begin with here, I think I want to add 1 to everything. So 0 plus 1 is 1, 2x minus 1 plus 1 is 2x, and 5 plus 1 is 6. So we find that 2x is somewhere between 1 and 6. Divide everything by 2 now. That's a positive number, so I don't change the direction. And I get a half is less than or equal to x is less than or equal to 3. So here we are on a number line, closed circles this time because it is greater than or equal to from half, 0.5 to 3. Righto, good start. Now, when we're dealing with quadratic inequalities, this is where the graphing comes back into it. Essentially what we do really is graph these quadratics. Okay, get rid of the greater than or less than symbols. Make it equal to 0. Now, I say here factorize, but that's just so that we can sketch it properly. Okay, sketch these things. You're really good at sketching quadratics by now. Sketch the quadratic and see where it is positive or negative as required. So we've got factorize it, set it to 0, solve it, find the boundary values. Right, that's going to be the bits where it's greater than or equal to. A sketch or a table of signs. Now, table of signs works okay. We're going to look at that for some, probably in the next video, for some slightly more complicated cases. I think with quadratics, we can quite reasonably sketch them and work it out. So, x squared minus 5x is greater than or equal to 0. Let's start with x squared minus 5x equals 0. We factorize that as x outside of x minus 5 equals 0. So this is concave up, roots at 0 and 5. Right? There's our little sketch. Now, where is my function greater than or equal to 0? Well, when it's less than 0, when x is less than 0, less than or equal to 0, and when x is greater than or equal to 5, that's where my function is above the x-axis. Right? What values of x? Right? I want to know when it's greater than or equal to 0. Right? If it's less than or equal to 0, or greater than or equal to 5, like that. Here's another one. We've got m's this time. So let that equal to 0, factorize it. That's enough now to sketch it from 3 to negative 1. The vertex doesn't mean much to me, or the axis symmetry for this case. Really, I'm just interested in the roots and whether it's concave up or down. You can interpret that purely from investigating the quadratic, if you like, that expression there. But let's say we sketch it here. 3, negative 1. Okay, and I want to know where my function is strictly less than 0. So between -1 and 3. Right, from -1 is less than m is less than 3 for any value there, and say I might put a 0 in. What happens if I substitute 0? 0 squared minus 2 lots of 0 minus 3. -3 is definitely less than 0. So as long as I choose a number that's greater than -1 and less than 3, okay, that inequality will be true. This time I am given a quadratic without a graph, and it's perfect square. I think we want to be a little bit careful here. So we'll let it equal to 0. That means that I have a double root, if you like, at x equals 4. It's concave up, looks like this. So when is that greater, not greater than or equal to, when is that greater than 0? Well, as long as x doesn't equal 4, it's greater than 0 for all other values. So that's my solution. X does not equal 4. I feel terrible about that working there. I've got consecutive lines where I say x equals 4, x doesn't equal 4. But we're sort of looking at different things. Bit sloppy. One to go. X squared plus 8x plus 3 is less than or equal to 0. Now, you can try factorising that, but you're going to see, if you use the discriminant, that I get an irrational number. So it does have 2 roots, but they're not rational. So I'm going to use the quadratic formula, and I find that x is -4 plus or minus square root of 13. If I sketch that, right, move my head out of the road, I get this thing here. Right, that's -4 minus root 13, -4 plus root 13. So I get this here, and I want to know when it is less than or equal to 0. So it is between, right, this point and this point. Right, these are this is where my function is less than 0. So from in between -4 minus root 13 and -4 plus root 13. Okay, right, it is a long video. Hold in there. This is a curious question, and we're going to draw in some knowledge that might have got a little bit rusty. Find the range of values of k for which this expression is always positive. I've got a quadratic, but with a second variable in there, k. And I want to know when that is always positive, when that's greater than, strictly greater than 0. Well, thinking back to our work on quadratics, we are looking for this description here. Always positive means positive definite. That is, the discriminant is less than 0, so it has no roots. It doesn't cross the x-axis, and a, the coefficient of the x squared term, is positive. So the positive part is fine. To be positive definite, I need my discriminant, that's b squared minus 4ac, to be less than 0. So discriminant less than 0, that means that b squared, right, -2 all squared, minus 4 times a times, it's a little complicated, is less than 0. So tidying that up, I find that that is true when k is less than 1. As long as k is less than 1, this expression will always be positive. Next up, and a fairly similar question really, explain why this is greater than 0 for all powers of x. Well, I can see it's concave up. It will be positive for all values of x if it is positive definite. We've got positive, now the definite bit. That means b squared minus 4ac is less than 0. Right? Less than 0 means it has no roots. So let's have a look at that. The discriminant is 4 squared minus 4 times 2 times 3, which is of course -12, which is of course less than 0, and that means it's a negative number. So a is positive, discriminant is negative, that means it's positive definite, it is always greater than 0. And here is a little sketch that I've provided. That is a sketch of the function, and you can see there that the minimum value there is when x is -1, and at that point my expression is equal to 1. Right, the graph is not really going to cut it as a solution unless you do the working to show all those other things. Anyway, that's it for absolute value, kind of, sort of, because our next video is also on absolute value. Okay, but this time we're going to look at polynomials and inequalities. Righto, that's it. If you've got any questions, please make sure that you ask me in class. There's plenty of time to do that, and I will see you there.